Hi, I'm Colin McCarthy. I'm a senior principal engineer here at Amazon Web Services. And today I'm going to talk about how we design with simplicity at Amazon. This is part of our Amazon Builders Library series. So if you're not aware already, actually we launched this at reInvent last year in 2019, where we've been building this repository, our library really, of interesting articles that are from first-hand experts here at Amazon on their experiences, building, designing, operating, running things, lessons we've learned over the years. There's all sorts of cool articles there. Go check them out. Probably across all those articles, you may notice a theme of simplicity. It's something we try to foster and encourage a lot at Amazon. In fact, it's actually one of our Amazon leadership principles. So we have a series of leadership principles. If you're curious about what they all are, you can, just search for Amazon leadership principles and you'll find the full list. But one of them is called Invent and Simplify, and we encourage ourselves and each other to constantly be inventing things for customers, constantly be innovating and coming up with new solutions for customers' needs and new cool things that we can offer them and delight customers with. But at the same time, we want to lean on simplicity, right? We want to make sure that as we build and engineer and create new things, that we don't add a huge burden of complexity that's going to weigh our systems down and both our technical systems and make them very hard to use and operate, or also, our business systems and just make it kind of hard to run our business for our customers. So we kind of pair those two themes together at the same time. As we're inventing, as we're innovating, as we're engineering, always be striving to simplify. But that's a kind of simplicity is a tough thing to really get into. It really begs the question, like, what do we mean by simplicity? What is simple? A lot of experienced, kind of hardened folks who've built a number of things do get to know and get a good feel for simplicity, get into a kind of it when you see it kind of state. But it can be pretty hard to have a very straightforward set of rules for, well, if you apply these tests and if you meet those conditions, then it's simple, then it's complex. People do try, and there's some common definitions and there's some common ways of thinking about it. Probably the kind of two most common ways to approach this is to think about, well, one definition of simplicity is things are simple when they have fewer moving parts, right? That's kind of a very engineering-y kind of approach, right? That's a very kind of mechanical way of thinking. You're kind of looking at the system and you're kind of literally counting moving parts, and you're saying, well, this system that has 2 gears is simpler than that system that has 10 gears, right? And that can feel intuitive. Fewer components means fewer things that can break, fewer things to understand, and so on. Another definition of simplicity that's very common is just simple means something's very easy to understand and easy to use, right? Something somebody can quickly adapt to and get a feel for. And I actually really want to emphasize that kind of second definition, that kind of humanistic definition of simplicity. And as we go through what simplicity means here at Amazon, I'm going to cover some examples of how we've built some systems that I think are simple, because I think a great way to really get a feel for simplicity is to look at examples and to learn from what others have done before, and to kind of see, well, how have those systems done over time? And the definition I'm using in my head is kind of that one, like how easy to understand and how to use were these systems over time. I think a really good illustration of this and why that definition suits me better and suits us here better at Amazon, and why this is what we mean by simplicity is, if you look at two designs for locomotion, right? A unicycle and a bicycle. A unicycle absolutely has fewer moving parts than a bicycle. like for sure. You can count them. It's got one wheel instead of two. Usually doesn't have gears, just pedals directly attached to the wheel and a stick and a seat, right? Incredibly simple machine if you're just counting moving parts. But there's no way that that's really a simpler solution for locomotion, for getting from A to B. Uh, a, a unicycle is incredibly hard to use. You got to have pretty good balance, and you got to have put in probably quite a decent number of hours to really master it and get to the point where you're not falling over, and you can get from A to B. Meanwhile, a bicycle, has two wheels, gears. There's more pieces of aluminium or steel involved, and any way you count it, it's got more moving parts, but it's a much more successful design, right? Yeah, it does take a bit to learn to ride a bicycle, but most even kids can do it in a day, right? You can learn how to ride a bike, and you can kind of ease your way into it with training wheels and so on. But after that, it's a very usable machine, very practical, and has stood a very long test of time. And so, I'd say a bicycle is definitely simpler and better than a unicycle if you measure it that way. You could extend that argument again and say, well, a tricycle with three wheels, that's even simpler than a bicycle, right? Because you can get right on a tricycle and get going. You don't need to learn any of the balance it takes to ride a bike. But then you start to see, well, the tricycle is probably a more complex system, and actually adding that extra wheel, creates all sorts of problems. Like it's just harder to store somewhere. It's harder to, maintain, all that kind of stuff. So simple often tends to be like some nice sweet spot in between a set of trade-offs. And if you were to look at these designs through just kind of the lens of mechanical elegance, the engineer, the mechanicus might just look at the unicycle and say, well, isn't that a beautiful, elegant machine? It's got very very few moving parts, and you can get going with it as long as you're willing to put the time in. But I think this example shows too that elegance can be really deceptive. You know, it's it's better to have that more humanistic take of, well, let's look at how it succeeds as a device actually being used in the real world, and let's have that be our measure of simplicity, because that is ultimately what matters. And why does that matter to us? Like, why do we value simplicity so much? I think our experience is that simplicity is highly correlated to some very desirable properties. Security is our top priority here at AWS, and simple systems tend to be easier to keep secure than complex systems. There's just fewer points of entry, smaller attack surface, if you want to think about it that way. There's just fewer places in a design where there can be mismatches between, one coder's expectations and another coder's expectations, and where you might have leaky abstractions and so on, where security issues can arise. You can help minimize all of that by keeping systems simple, right? We also value durability a lot. We don't never want to lose data, right? And so we want to have really simple, robust mechanisms that are making sure that we're not going to lose any data. Reliability, we value that incredibly highly. And what I said earlier is still true. The fewer moving parts you have, the generally less that can go wrong. My example covered how too few moving parts can be a bad thing, but you still want to have as few parts as you really need, right? Because you want your system to be reliable, and you don't want to have, you don't want to have a huge number of components where if any of them go wrong, you're in trouble. Simple also tends to keep costs down. Simple systems usually easier, faster, cheaper to build, and so we can pass on all those savings and have cheaper offerings, which everybody likes. And they're also just simple things are just easier to manage. I mean, that's almost a tautology, right? The way I'm defining simple is by saying it's really measured by how easy to use, operate, and manage things are, and that's just always a desirable thing in any line of business. And then the other kind of reason why I think we want to emphasize simplicity so much is just because we kind of think, Well, we're still in the early days of the internet and like online systems and highly available systems. And we always want to be first to find those really great solutions and components that are going to, really stand the test of time. The things that are going to be reused over and over and over for decades, and power the industry and make sure that, um, we can just have, incredibly highly available and very highly secure systems that can be used in all sorts of walks of life and business. And being able to get to that quicker is, um, just a huge, uh, saver for everybody, right? It just advances the whole industry forward, much more quickly. It's um, it's a big key to our long term success. And just a fact of life, at least, working here at AWS, is that, we've been growing quite quickly as a business as long as I've worked here. I joined in 2008, and so you're kind of just constantly hiring folks and expanding and growing teams, and the set of folks who are on a service team, 3 or 4 years from now might be very different from the set of folks now, and so just constantly trying to build systems that are going to be sustainable and maintainable and work across those boundaries. So I'm going to cover 5 examples of simple, like I said. So each of these examples, I've kind of picked them from our history. They're a diverse set of examples that cover different things, but what they each have in common, I hope, is that they've actually stood a test of time and have helped customers solve problems. And the first example I want to cover is availability zones. And so, before availability zones came along, right? Before we had availability zones, customers and also we ourselves, would struggle to really think about, how do I build meaningful resilience and redundancy into my system. I know that I need to have, some redundancy or failover capability, but I also need to make sure that, like, if I'm going to have a problem, it can't happen to, both my primary and my secondary at the same time, right? That would be bad. I would have an outage, and no one wants that. But I also might have other layers and other systems that have the same requirements. And so how do I reason about all of these at the same time? And I need to think hard about shared fate and about avoiding it. And so, there are things, they don't happen very often. We're incredibly good at managing them, but there can be power issues or networking issues that could take out an entire, building at the same time. Or there's extreme weather events or earthquakes and so on, things that are completely out of anybody's control, that can also impact things at the level of a physical location. And so builders just need to be able to reason about all of those. Availability zones are just an amazing simplifier, right? Instead of having to think about this gigantic sea of infrastructure and checking every single little node that you pick, well, is this one really redundant compared to this other one, or do they possibly shared fate? We just instead have availability zones, and we tell customers, hey, if you've got 2 things in this same availability zone, they could have a problem at the same time, in theory, someday. So don't make one redundant for the other. That that's not going to work. Very easy to understand and use, in my experience. We reuse this concept over and over, right? So we invented it because of the core low level infrastructure risks like power networking, as I mentioned. But we figured, well, since we have it, we might as well also use it for things like deployment risks, right? And so when we deploy new software, we do it just to one availability zone at a time, right, in a given region. And so if there's any problem with that software, it can only impact that one availability zone, and customers still get the benefits of availability zones. We've done other things over time too, like occasionally we've aligned hardware types, with different availability zones. Like, you might use, a component made in a certain factory or by a certain manufacturer in this availability zone, but not the others. Just so that if there's any kind of correlated issue or problem with that hardware type, that also gets the benefit of kind of the availability zone design, which is really neat. Over time, we've actually even learned to simplify this concept further. When we first made availability zones available, it was actually um, you know, you as one customer might get, US East 1A is a certain physical building and a certain physical data center, but my US East 1A is a different physical building and a different physical data center. And the reason for that was we were a little worried that, like, well, everyone might just choose A because it comes first in the console, and we'll get all this infrastructure just landing in the same spot, and we'll have this terrible imbalance of resources. And so we kind of randomized it a bit across accounts. Turns out over time, customers understood availability zones and got really good about placing infrastructure diversely, and in their tools and other tools we built would just kind of naturally spread things. And so we didn't need that anymore. And so we were able to kind of change to a model where, for new accounts at least, everybody's A is the same, everybody's B is the same. And so you can even reason about these availability zones across customer accounts, which is another nice simplifier. So my next example is in a totally different area. So that's all about like physical infrastructure and how we model redundancy and keep things separate. My next example is actually related to security, and it's the SigV4 authentication protocol that that is what powers authentication and authorization for almost every API request that is made to an AWS service. So as you can tell from the name, SigV4 is not our first attempt at an authentication protocol. We had some others before. Actually, really only SigV2 got significant usage outside of Amazon. But we've made refinements and simplifications across time and landed on SigV4 quite a long time ago. I think over 10 years ago now, and it is there as like the core way all API requests are authenticated, but it's also available to customers. So if you want to use SigV4 to authenticate your own requests, you can. It's part of API Gateway. And I think what I find simple about SigV4 and why I think it's kind of stood a really good long test of time is it uses cryptography, which is normally a very complicated, complex thing. And you see a lot of changes in cryptographic systems over time. If you think about SSL or TLS, people are going through many versions and choosing different algorithms and so on. With SigV4, it's actually implemented in an incredibly small amount of code. It's a very simple algorithm. You could write an implementation of SigV4 in a few hours. If you're a programmer, and we have the specification published. If you ever wanted to replicate it, it's all built on top of a cryptographic algorithm called HMAC SHA-256. I'm not going to explain what that is or how it works under the hood, but you can go through our diagrams of how SigV4 works if you're curious on the website. But at a high level, we take a request when it comes in, we canonicalize the request headers into a canonical order. Then we derive some signing keys from like the current time, the region, the AWS access key, does all of this, uses that HMAC algorithm that I talked about, and authenticates the request. And for something like authentication, it is stunningly simple. There's very little going on. It's very robust. And that also means, there's just very little surface area exposed for any kind of potential security issue, before a request is authenticated. And it's been really cool. And I just wanted to call it out as a kind of example of a really simple design that's kind of survived a good, nice test of time. So the third example kind of brings us back to traditional infrastructure resilience and redundancy a bit, and that's DNS health checks. So a long time ago, we decided to make our own services extremely highly available and reliable, that we would use DNS health checks as this kind of core primitive for ensuring things are highly available. And we actually built DNS health checks directly into Amazon Route 53. It's a feature you can use as a customer, and many do, and use it very successfully. But we also use it ourselves a lot, right? So Amazon Elastic Load Balancing, relational database service, and other services are actually creating and managing Route 53 health checks on customers' behalf. And that's how they're ensuring that, if ELB nodes have an issue, it's DNS health checks that step in and route around that issue. Or if an RDS primary database has an issue, for example, it's DNS health checks that kick in and make sure that the secondary takes over. And because these health checks are happening all the time, right? Route 53 is constantly health checking these targets. Whether it's your own EC2 instances or ELB nodes or RDS instances, because it's always happening. It's a very highly reliable system. If we even have, say, an entire availability zone suffer a power issue, and so we lose power and those instances become unavailable, those DNS health checks notice right away and stop routing traffic right away to those instances. There's no need for us to make any API calls or reconfigure Route 53 in any way. It just does it without intervention. And that's been something very simple that we've been able to build on top of over and over, and strongly contributes towards the high levels of availability we've been able to achieve. So the next kind of simple pattern that I love and see a lot at Amazon is rollback, by which I mean, when you're writing code at Amazon, obviously you're expected to write good code and make your best attempt to write something that's bug free. But none of us are perfect, especially me, and so we all make mistakes. And then the next kind of process that steps in is, well, code review and testing, and as a team making sure that we're catching problems before they ever get to production. But as hard as you try to get to perfection there's just always some risk that there's something in your code that when you finally do push it to production, you're only going to notice then, because it's triggered by maybe a very rare set of circumstances that were hard to cover in testing, but occasionally a few customers might trigger, or just some difference in the infrastructure or nature of production itself, or triggered by extreme amounts of load and so on. And so we invest a lot in deployment safety here at Amazon. We have builders library articles about that. So we like to stagger our deployments and start small and increase the deployment size as we get more and more confidence in it. But what we've also learned is that actually fast rollback at every stage is a really good key to success. And if we ever hit operational problems, pretty much the first question we're always asking is, okay, let's roll it back. We're not going to waste time investigating why it's failing. We're just going to observe, hey, there was a recent change in this area, so let's roll it back. And we've kind of baked that way of thinking into our team culture pretty deeply. Teams and developers know that if I'm building a change or getting a new version of my software out there, it always has to be ready to roll back. And I have to think about that and be prepared for that. So for example, if I'm doing something like making a schema change, which is sometimes a breaking change if you do it very naively, you can't really do that at Amazon. You have to split it up into a phase change where you add a new column or whatever you're doing to the schema, and then you write in both the old format and the new format for a while, so the rollback would always work. And then you push out another version that stops writing to the old one, but you could still roll forward and roll back even for that deployment if you wanted to. So it takes a little bit more effort to, get your full change out there. It takes a few more steps, but we value rollback so much that we go to that effort and we kind of insist on it. And then the last example I wanted to cover is something we call static stability, which again you can find in our builders library articles. And the concept of static stability hopefully will sound very simple. It's essentially, if a system does lose power or networking, it should come back more or less to the state it was previously in before that power event or before that networking event. There are a few exceptions to that. Things like, a primary database may have flipped away to a secondary, and if power comes back, you don't want it to become primary again right away. That's not appropriate. But you do want the machine to boot and work, and the application to start, and health checks to start passing, and on all of those kinds of things. And this is harder than it looks, especially when you're building highly distributed systems, especially when there's all sorts of dependencies you could be using and depending upon. And you got to think carefully about, well, what if they're not quite available yet as I'm booting? What if they also were impacted by this same event? There's a really, really tough case of this for encrypting durable data, where let's say you want to encrypt all the data on a machine, right? Well, that means you need the encryption key on that machine, right? Well, you can't store the encryption key in the encrypted volume. That doesn't make sense. Then that's a circular dependency. When you first boot the machine, how would you decrypt the volume? You don't have the key yet, right? So you have to keep the key somewhere else. A traditional solution to this is, well, we're just going to hide the key. We're just going to stash it somewhere on a plain text volume that isn't encrypted, and we're just going to give it a name that's not easy to figure out or whatever. But then security engineers don't like that. Security engineers are like, that's terrible. You can't. That's not appropriate. And then the other solution then is, okay, well, I can't keep it on box. Then I'll use it in memory for decrypting the disk as I need it. But otherwise, it's just not going to be on the box at all. And when the system boots, we're going to fetch that key from some key management service, right? And the key management service will authenticate me somehow and give me the key, and then I can decrypt the disk. But that's not a particularly statically stable pattern. What if you boot but the key management service isn't ready yet, right? So that thing gets that gets pretty hard. So we've invested to the point where our AWS Nitro security chips, which are now baked into our EC2 platform, can actually they have this secure enclave baked in that can actually just keep these keys in a way where they're not accessible, but they can be used. And so you can manage this trade-off between security and availability, and you can have static stability. When the system boots, it can actually get the key because it has a copy of it in this enclave and do the disk encryption and disk decryption that it needs without needing to worry about it, which is nice. A tremendous simplifier. That's my last example. Hopefully, from those 5, I've covered some kind of inspiration for what simplicity really means to us and how we think about, just keeping things nice, plain, and usable. Hopefully you've taken away that humanistic meaning I've been emphasizing, that we really want to focus on how these things work for people. We want to build systems that are as use as few moving parts as necessary, right? That'll be filtered through a kind of survival of the fittest process. If something doesn't have enough components, if it can't cope with a stressful event, we'll eventually have to add a component to make sure. And I'd say, study more examples, find them anywhere you can. Other technology providers, other folks out there who've shared their own, study those too, because I think it's the best way to learn, and share them with me too. I'd love to always find more examples. Thanks for following along. Thanks for watching everything in this talk. It really helped me, and it really helped us. If you could also fill out the session survey, it lets us know what everybody's interested in and how we can improve and refine all these talks for future new versions and so on, and what you want to hear about. Thank you again.